Alright, so section 12.8 is on graphing different trigonometry functions, and more specifically how to translate them, so how to move them right and left, up and down, vertically stretch, vertically shrink. And that's something that we've talked about in earlier sections as well, but it's good to know how to apply that to specifically the trig function graphs. Okay, so first of all, this is a kind of a picture of just an example of shifting a sine function or a cosine function. And you can see you have a bunch of numbers here. So this number here is going to tell you whether it's going right or left. This number here is going to move the period. So it's going to make it either cycle through a complete period more often or less often. This number will vertically stretch or shrink it. If it's larger than 1, it stretches, and less than 1, it will shrink. Okay, so you can see some pictures here, but rather than go through that kind of a mess of a picture, I think it's easier to do some examples. You'll see them as we go. Okay, so this says state the amplitude, period, and phase shift for each of these. Well, like we talked about in an earlier section, the amplitude is the number that is in front right here. In this case, there's just a 1. So the amplitude in this case is just equal to 1. Okay, the period is, we take this number here, which is also 1, and we divide it into 2 pi, or into 360 degrees. So since they're giving us degrees, let's work in degrees. So 360 divided by 1 is just 360. What that means is it's going to go through a complete cycle once every 360 degrees. So we found the amplitude, we found the period. The phase shift, you might remember from an earlier section, from a bunch of earlier sections, the saying add to x, go left, and add to y, go high. Add to x, go left, add to y, go high. Well, in this case, it's not really x, it's theta, but the same idea applies. Adding to x makes us go left. We're subtracting from x. So that means we're going to go right 90 degrees. So this graph, when we graph it, it's going to look exactly like the graph of sine, except we will go to the right 90. So in order to do this, let's first graph what sine looks like. And here's a unit circle, just to recall. On the unit circle, we have these coordinates right here. We have 1, 0. Remember, I'm getting these numbers because the unit circle has a radius of 1. So these are all going to be some version of 1, either positive or negative 1. And the sine is the y coordinate. So the sine of 0 degrees is 0. So let's just fill this in. So here's 90, here's 180. These don't have to be drawn to scale. I'm just kind of doing it every 3 dots here. There's 270, and there's 360. Okay, and we're graphing the parent function first, so the sine of theta. So the sine of 0 degrees is 0, so let's put a 0 right there. Let's make this 1, and we'll make come down here for negative 1. The sine of 90 degrees, this is 90 right here, the sine of 90 is 1. So that's the point right here. The sine of 180 degrees is 0. And the sine of 270 degrees is right here at negative 1. And then finally, we're back where we started. That's 0, and that's also 360. So we just showed one complete period right there. Our starting point is here. Our ending point is here. Okay, how do we graph this new function right here, this sine of theta minus 90? Well, the amplitude and the period are the exact same. The only difference is take all of those points and shift them to the right 90. So this point was at 0, 0. I'm just going to bump it to the right 90. This point was at 91. I'm going to bump it to the right 90. So now it's at 181. This point right here was at 180, 0. If I bump it to the right 90, now it's at 270, 0. And finally, this point right here, that was at 270, negative 1. 270 degrees, negative 1. If I bump it 90, now it's at 360, negative 1. Oops, that's not negative 1 right there. 360, negative 1 would be right here. And then this last one is going to get bumped another 90. So let's kind of connect these now, and you can see that green graph right there is just the red one shifted to the right 90. So that's not so hard to do when it's a basic shift like that. Occasionally though, the shifts are not quite as clear cut, so I'll show you how some of those work as well. Okay, and that's what the graph looks like, just a little bit more neat than I had it. So they moved it to the right 90. You can see they showed you that left part of the graph too, but what we had is fine too. They just took this point and they shifted it to the right 90, but otherwise the graph is the exact same. Alright, not only can we shift it right and left, we can also shift it up. So they're giving you this example with a parabola. And I want to show you two examples here, A and B. Let's say this is x squared plus 5. This is x plus 5 squared. So you can see those look very similar. This one, though, moves it up 5 because you're adding to y. Y is this thing. Y is x squared. That's the parent function. You're adding 5 to that y value, to the x squared. So that means you're moving it up. Here, you're adding to x. So that would mean go left 5 because the plus 5 is almost attached to the x. It's inside of that function and it happens before you square it. So that's the difference. So vertical shifts work the same way. You just bump the graph up and down instead of right and left. And you can see some pictures with cosine there. And then when you do that, you also want to be aware of something called the midline. The midline is this line right here. It's the line that cuts through the graph, and it's essentially the average of the high point and the low point. So for example, suppose that right there was 8, and suppose this right here were -2. You would find the midline by finding the average, which means add them and divide by 2. 8 plus -2 is 6, and 6 divided by 2 is equal to 3. So that means this midline would be y equals 3. The distance from 3 to 8 is 5, and the distance from 3 down to -2 is also 5. So that's how you know that it's the correct midline, if the distance from the peak is the same as the distance to the low point. Okay, so let's do this graph now. It's not a horizontal shift, but this time it's going to be a vertical shift down too. So the amplitude is always this number right here, which is 1/2. The period is always the number in front of theta divided into 360. So in this case it's 360 divided by 1, which is 360 degrees. So same period as normal. And then this one right here, add to y, go high, we're subtracting from y, so we're going to go down 2. Okay, so what I'm going to do is graph the regular cosine function, and then we'll just take that and shift it around in order to get the other one, or I should say the transformed version. Okay, so let's do that. So we will have, let's just see the best way to do this here. Okay, let's try this. So we'll get our main angles again. So 0 degrees, 90 degrees, 180, 270, and then 360 is a full period. Okay, this will be, let's make that 1/2, and let's go by, actually let's do this instead. I'm just trying to think of the best way to make this graph clear. Let's make each of these be 1/2. So that's 1/2, that would be 1, that would be 1.5, that would be 2, and then we'll follow the same pattern right here. So this is -1/2, this is -1, and let me just move this up a little bit. This will be -1.5, and that will be -2. So cosine on the unit circle is the x coordinate. So here's our unit circle, 1, 0, and -1, 0. And this point is 0, 1. And this is 0, -1. And remember, this is 0 degrees and also 360. This is 90 degrees. This is 180. This is 270. So let's graph the parent function just so we can have that as a model. So the cosine of 0 degrees is 1. That's right here. Cosine of 90 degrees is 0. Cosine of 180 is -1. That's right here, and the cosine of 270 is also 0, and then 360 is back where we started. That's a full period. So here's what the graph looks like. It looks really the same as sine. The only difference is you've kind of shifted it. It's like a shifted version of sine. Okay, now what are we doing with this transform function? Well, first of all, we're shrinking it. We're taking a half. So that means all of these functions, all of these coordinates are going to be taken half of. So the 1 right here is now going to go to half. And I'm not going to fill these in yet. I'm just kind of, when it's half of 0 is still 0. Half of -1 is -half. Half of 0 is 0. And half of this 1 is half. Okay, the reason I didn't quite fill those in yet, though, is because we first shrink it, and the order is important. We first shrink it, and then we bump it down 2. We move it down 2. So I'm going to do that in green. So if we took this point and moved a half down 2, well, that would move it down a half. We have to move it down another 1.5, so right there. If we move this 0 down 2, that's going to put us at negative 2. So right here. If we move this negative half down 2, we're actually going to be down at negative 2.5, so that is right here. If we move this 0, well, we're still at 0. Sorry, if we move the 0 down 2, I should say we're at negative 2. And then finally, if we move this one down, we should be back where we started, which is negative 1.5. So you can see when we connect the dots here, first of all, it's not this distance right here, the midline distance from here to here is 1, from here to here is 1. This midline is going through negative 2, because negative 2 is where we moved it down to. And the midline here is only a half this time, or from the top to the bottom. And the reason it's half is because our amplitude is 1/2, the number in front of cosine. So that's how you can do it using transform. Just graph your parent function, and then afterwards you can shift it as needed. Alright, so those are kind of the simpler versions. Let me show you the more complicated version now, and that's when you're doing a whole bunch of shifts at once. Okay. So here's kind of what that looks like. So you can see each of these things right here. This tells you the right or left. This number tells you the up or down. This number tells you vertical stretch or shrink. And this number is the period. You divide that by 360. So they give you a bunch of steps here. I have this sheet that kind of goes through the steps. And you don't necessarily have to do step 1. It just kind of tells you a basic way to set it up. But then I'll explain, this is the important part, making a table of values, and we always start our table of values at whatever number makes the parentheses, and the parentheses meaning the thing right next to, in this case, sine, where it says sine of 3 parentheses theta minus 180. What would make theta minus 180 equals 0? 180 would make it 0, so we would start our table at 180 like it says there. And then we get the next x values by dividing the period by 4, and that may not make sense now, but it hopefully will when we do an example. So let's do a complete example like this with all sorts of shifts. We don't want to do the method we use on the other two because it's not going to be easy to tell. So first of all, let's change this into degrees. So that's the same as 180 degrees. Easier to usually think in degrees. And our first step is to make a table of values. I mean, it says to find the amplitude and stuff, but we kind of know that the amplitude is 3, but we should find the period. No, the period is going to be 360 divided by this number. So dividing by 2 over 3, that's like multiplying by 3 over 2. 2 goes into itself once, and it goes into 180. Sorry, it goes into 360 180 times. 180 times 3 is 540 degrees. So that is our period. Okay, the phase shift is going to be minus 180, so that's to the right 180. And then this plus 4 is going to move it up 4. So let's do this. Let's just fill in this table of values. And I said, in just a second, I'm going to show you why we have to, or how we get the other values. So we know we're going to start our table at whatever makes the parentheses 0. So what makes this parentheses 0? Theta minus 180. Well, 180 would make that 0. Okay, so we're going to plug in 180, and then let's see what happens here. So 2/3 times, if we plug in 180 here, we get 0. The sine of 2/3 times 0, that's just sine of 0. Sine of 0 is 0. 3 times 0 is 0, and 0 plus 4 is 4. So our first coordinate should be at 180, comma 4. So here's 0. Let's call this 90. Let's call this 180. Actually, let me make this a little bit smaller because this period is going to be 540. So we're going to kind of run through it. It's going to take a little bit longer. So 180, this will be... actually, we'll wait to fill this in. I'll show you why in just a sec. So we know our first point is at 180, comma 4. Okay, next question. How do we fill in the rest of the table? And here's what this says. Okay, this is this part. It says each subsequent x value should increase by the period divided by 4. Why do you divide the period by 4? Here's why. And if you can understand this, I think the rest will make sense. So here's our unit circle. Notice how many significant points there are on this graph. There's one significant point at 0. There's another significant point at 90. There's another at 180. There's another at 270. And then we come back where we started, so we're at 360. So the reason, and I didn't put it here, but the reason my table has 5 things in it, 1, 2, 3, 4, and 5 is because there's kind of 5 significant things. There's 0, 1, 90 is the second, 180 is the third, 270 is the fourth, and then we want to include 360 just to show that we wound up back where we started. Okay, why do you divide the period by 4? Because there's 4 significant things. There's one significant thing at each of those 4 points right there. If we do this correctly, if we fill in the right x values, then all of those numbers that you see there, 0, 90, 180, and 270, those should be getting plugged in to this function right here. So how do we do this? We take our period, which is 540, and we divide it by 4. Why again are we dividing by 4? Because there are 4 significant places on this graph at 0, 90, 180, and 270. And that number when you divide by 4 is 135. So that means for each of these, we are going to be increasing by 135. And it's the same thing right here. On this function, the traditional period is 360. So if we were to divide 360 by 4, we would get 90. What are we increasing by? Well, to get from 0 to 90, we're increasing by 90. To get from 90 to 180, we're increasing by 90, and so on. We're increasing by the period divided by 4, which is 90. So in this case, our period is 540. If we divide that by 4, we get 135. So 180 plus 135 is that. 315 plus 135 is 450. Okay, then 450 plus 135 is going to be 585, and then 585 plus 135 is 720. We set a period as 540, so from 180 to 720, that's 540 degrees. So let me kind of draw this on the graph. So this, we'll call this one right here 180. And you can see why I didn't fill these in before, because we need to know first what this is. So this is 180, this is 315. This is going to be 4, like counting those correct, 1, 2, 3, 1, 2, 3, 1, 2, yep, that's 450. This is 585, and this is 720. So this, the reason we're labeling this is just to make sure it's drawn to scale. And this is 1, 2, 3, and 4. So our first point is at 180, comma 4. So that puts us right here. And then we're probably going to have to go, actually we shouldn't have to go negative because we moved it up 4. Okay, now how do we get the rest of this? Now we just need to fill in our table of values. And the way that we do this is we take these values and we plug them in right here for theta. So 2/3 of 315 minus 180 plus 4. Okay, 315 minus 180 is 135. So we said if we're doing this correctly, our values 0, 90, 180, and 270 should be getting plugged in. So let's verify that that happens. 2/3 of 135 is actually 90 degrees. So that's a good sign that we're getting 90 plugged in. Sine of 90 is 1, and then 3 times 1 is 3, and then 3 plus 4 equals 7. So our next point should be at 315, comma 7. And that makes sense because we took this graph, we shifted it up 4. So 5, 6, here's 7. And we have a point at 315 right here. Alright, then our next value, 450. Now again, if we're doing this correctly, we got 0 plugged in right here. We got 90 plugged in right here. If we're doing this correctly, then plugging in 450 should result in 180 getting or showing up here. So let's verify that. So 2/3 times 450 minus 180. And just one thing that comes to mind while I mention it, in the original problem they gave us the 2/3 factored out right here, but if you ever had a problem where they didn't, so suppose they said y equals sine 2/3 theta, let's say, I'm just making this up, minus 50, let's say, you would not want to start doing this until you had first done this, until you had first said y equals sine 2/3, you pull that out, and then it's theta minus, and then you have to divide that by 2/3. So dividing that by 2/3 is like multiplying by 3/2, and that turns out to be 75. So whenever you're doing these problems, make it look like this. Make sure the 2/3 or whatever numbers in front is factored out, because you know if you look at this, this tells you to go right 75. This means go right 50, or it looks like go right 50. So it's going to confuse you unless you pull the 2/3 out. But that was already done for us in this problem, so that's just a side note. Okay, let's see if we do this correctly. So this 450 minus 180 is 270. So we're taking 2/3 of 270, and that turns out to be 180. And that checks that box because we want 180 to show up here. one other thing to notice, we're supposed to take the sine of 180 times 3 and then we do the plus 4 at the end. This is not 180 plus 4, this is sine of 180 and then afterwards plus 4. So the sine of 180 is 0, 0 times 3 is 0, and 0 plus 4 is 4. So we have a point at 450 degrees, comma 4, so that puts us right here. So this is starting to look like a sine graph like it should. Okay, 585. So if we do this correctly, now 270 should be plugged in. And actually this last point 4, we already know this is going to be 4 because from 180 to 720 is a complete period. So we don't even need to calculate that. You can if you want to verify, but it will work. Okay, let's plug in 585 here. 585 minus, what was it? Sorry, it was minus 180. 585 minus 180 is 405. Oops, let me use a different color here. So this is 405, and 2/3 of 405 turns out to be 270, and that is exactly what was supposed to show up. The sine of 270 and then plus 4. The sine of 270 is -1, and 3 times -1 is -3. -3 plus 4 is equal to +1. So 585 comma 1 puts us right here, and then 720 comma 4, that was the last point, puts us back where we started. So if we connect the dots right here, so we move it up a little bit, so we end up getting this picture, sorry, right here, not drawn the best, but let's verify. So that looks like a sine curve that is amplitude's a lot higher, right, because the normal amplitude is 1. This amplitude, the midline right here, I don't know if they asked us for it, the midline should be the top 0.7 plus the bottom point -1, and then the average of those, so this equals 3. So let's verify. The midline then would be this line right here, which cuts it in half. The distance from 3, sorry, did I do that correctly? Sorry, that's supposed to be a +1, not a -1. So it actually should be 7 plus 1 is 8, divided by 2 is 4. So wrong midline here. The midline is actually at 4, which is going to be right here. There's the midline. The amplitude from 4 to 7 is 3, and from 4 down to 1 it's also 3. So that checks off right here. It's been shifted 180 to the right, so that's right here. It's been shifted. And then we moved it. You can see it's been moved or translated up 4. So that was a long process. But the main idea is to fill in that table of values. You start with the number that makes the parentheses 0. It was 180. And then the way that you get from one to the next is you increase the period divided by 4. Why divide by 4? Because on that unit circle there are 4 significant regions: 0, 90, 180, 270. And if you did it correctly, you can see those numbers are going to show up when you make your table of values, which they did for us. Okay, last one that I want to show you is, let's see, make sure we're doing this correctly. So sometimes they might give you a situation and say write a function for this. So let's write, in this case, a sine function, because they're telling us to write a sine function with this stuff plugged in right here. Okay, so this is basically what they're asking us to find. We have to plug in all these values. So first let's start with the amplitude, a maximum of 13 and a minimum of 5. So let's say you have this wave or something. This up here is 13 and the low point is 5. Okay, how do we find the midline? Well, we did it before. We just find the average. So 13 plus 5 divided by 2, that's going to equal 9. So this midline right here is y equals 9. That means that the graph has been shifted up 9. Just to remind you, like what we did on the other one, whereas if the midline here was equal to 4, that's because we had shifted this up 4. So the midline is always the amount you shifted up. That means this k value should be, the midline should be 9, which we just found. Okay, so we have that. That means the vertical shift is 9. Find the amplitude. Okay, well the normal amplitude is equal to 1. On a regular sine function, the amplitude is 1. Okay, the amplitude right here is basically what's the distance from 9 to 13 right here, or what's the distance from 9 down to 5, and the answer would be 4. So the easiest way to find the amplitude is just subtract the high point from the midline. So 13, you write that here, amplitude is going to be 13 minus the midline, and then divide that by, sorry, not divide by 2, just find that outright, which is 4. So that means this number here would be 4. Okay, the period is always 360 divided by this number, so 360 divided by b. But since we're dealing with a word problem with actual real life like feet and inches and stuff like that, let's change. Instead of using 360, we'll use radians, so we'll use 2 pi. Okay, what would, or how would you do this in this case? Well, in this case we want to find, they're dealing waves per minute, so let's change that to, let's find out how many waves there are in seconds. So 6 waves per minute, 6 waves per minute. That's the same as 6 waves per 60 seconds, and that means a wave every 10 seconds. So that means every 10 seconds this thing is going to go through a complete cycle. So that means 2 pi over b is equal to 10. 10 seconds is basically how long it takes for this generator to pump on a wave. So let's solve for that. We will get 10b is equal to 2 pi. And we will divide both sides by 10. So b is 2 pi over 10, which is the same as pi over 5. So let's replace this with pi over 5. And then they don't tell us anything about shifting to the right or the left at all, so we really don't even need this minus h right here. So our final answer should end up equaling this right here. Okay, it says find the height. We pretty much found it right there. That's our function. And then in terms of graphing it, it's much easier to graph this one on a, could go through that process we did before, but let's just show you how to graph it on a graphing calculator. So here's what you would do. You go to y equals, and we will just clear all this stuff out here. So we'll do 4 times the sine of, we got to make sure we get the right parentheses, pi over 5 theta. So we'll do second pi divided by 5, and then I have to include this in parentheses because if not, you put parentheses. I'm going to do second insert parentheses. The reason you do this is because if you just put the x right here, I'm going to use x instead of theta. If you put the x without the parentheses, it's going to be pi divided by 5x, and that's not what you want. You want pi divided by 5, that whole thing, times x. So I'm closing that in parentheses, and then we have plus 9. Let's graph it. That's not a good picture. So let's change this so we have zoom. We'll do zoom standard first. Still not a great picture, so let's do zoom fit instead. And yeah, that's still not working, so let's see what the issue might be here. Okay, let me try this. We'll go to graph. Let me zoom out. I think I might know what happened here, but not quite sure. Okay, yeah, now you can see, sometimes you have to zoom out a bunch to be able to see the function, but there's the function right there, and you can do stuff like this if you wanted to find, you know, the height. We said the highest point should be 13. You can see that's pretty much on 13. If you wanted to, I mean, let's suppose, for example, you wanted to find out y equals the height of the water. Let's suppose we want to find out at what time does and actually this, sorry, I don't know why I was using theta. That should be a t for time. At what time does the height of the water equal 10, let's say? When does it equal 10? So here's what we could do. We could do y equals 10, and then we'll graph that. And let's find this first intersection point. So second calc, they didn't ask us to do this, but it's kind of useful to know. So enter, 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 and it looks like at 23 seconds. So remember, every 10 seconds it goes through a period. At 23 seconds, the wavelength, or the wave height, will be 10. That's how you could use that for a word problem. So that is section 12.8 on how to graph trig functions.